limit x tends to c, f of x equals L. This L is called the limit of the function f as x tends to c. But what does it actually mean in the language of mathematical analysis? Let's break it down. First, see the part right here, x tends to c. This is telling us that x is getting closer and closer to the value c. Just imagine here is a point c in the number line, and suppose there is a delta greater than 0, which is an arbitrarily small number. Think of this delta as small as you please, but just must be greater than 0. Now we move little bit to the left. Here is c minus delta, and we move little bit to the right. Here is c plus delta. So as x approaches c, then x must belong right in this interval. We call this the neighborhood of c and denoted by b c comma delta. So what this symbol is actually telling us is that as x approaches c, x must belong in this interval, c minus delta, c plus delta. X belongs just right here. X belongs here. So if x belongs in this interval, then we can write it as x is less than c plus delta and x is greater than c minus delta. Subtract c from all sides, we get x minus c, and delta is right here. We can write this as modulus of x minus c less than delta. This right here is the mathematical representation of x tends to c. This makes sense because as x is getting closer and closer to c, the difference between them is getting smaller and smaller, which is very close to 0. We denote this value as delta. And now similarly, think L is right here in the number line, and there is another arbitrarily small value, epsilon greater than 0. This is just like delta, which is very close to 0 but just greater than 0. And right here is L minus epsilon, and here is L plus epsilon. Now by similar reasoning, we can get to the conclusion that f of x minus L modulus is less than epsilon. That's it. We broke it down. As x tends to c, f of x equals to L. What this means is, as x minus c modulus is less than delta, we must get f of x minus L modulus is less than epsilon. And this epsilon and delta are arbitrarily small value. They can be as small as we please. As small as we please. Now let's write this definition in purely mathematical form. If for every epsilon greater than 0, there exists some delta greater than 0 such that x minus c modulus less than delta implies f of x minus L modulus less than epsilon, then L is said to be the limit of function f as x tends to the point c. Okay, let's see an example. Verify limit x tends to 1 root under x plus 3 equals to 2 using epsilon delta definition. So according to this question, we have got f of x equals to root under x plus 3. And our limit L right here is 2, and the value c we used in our definition is equal to 1 in this question. So to prove this using epsilon delta definition, first we suppose there is given epsilon greater than 0, some epsilon value exists, and f of x minus L modulus must be less than this epsilon. So we can write it as root under x plus 3 minus our limit 2 modulus less than epsilon. Suppose for any given epsilon greater than 0, the modulus root under x plus 3 minus 2 is less than epsilon. That is x plus 3 minus 4 over root under x plus 3 plus 2 less than epsilon. These two inequalities are equivalent to each other. I have jumped one step here because see, root under x plus 3 minus 2 we can multiply by root under x plus 3 plus 2 in the numerator and denominator, and when you do that we get a minus b, a plus b. This is in the form of a minus b, a plus b. When we multiply them we can get a square minus b square under x plus 3 plus 2. So when we square it we get x plus 3 minus 4 upon x plus 3 plus 2. So I have jumped this step and written exactly that. Or you can write this as x minus 1 modulus less than epsilon times modulus x plus 3 plus 2. Now choose delta equals to epsilon times x plus 3 plus 2 greater than 0. That means we can write x minus 1 modulus is less than delta. We have chosen delta as epsilon times root under x plus 3 plus 2 modulus. So as epsilon is arbitrarily small number, this epsilon times this value is also arbitrarily small, and we have chosen that value as delta. So what we did right here is we suppose that for any given epsilon greater than 0, our function value root under x plus 3 minus our limit value 2 modulus is less than epsilon. So for any given epsilon, f of x minus al is less than epsilon, and we continued solving from there, and later on we obtained that modulus of x minus 1 is less than some arbitrarily small value delta. So this means for every epsilon greater than 0, there exists some delta greater than 0 such that x minus 1 modulus less than delta implies root under x plus 3 minus 2 modulus less than epsilon. So 2 is limit of root under x plus 3 as x tends to 1. That's it. We have verified this limit purely using epsilon delta definition only. We suppose that there is some epsilon for which our function value minus limit value is less than epsilon, and we found our delta which is related to epsilon by this equation right here, and we obtained that the modulus of x minus 1 is less than that delta. which means 1. As x approaches 1, our function value approaches 2. So this is the limit. Thank you guys for watching the video.